Hello classmates, this is the last lab of our course LAB5, Choose Your Own Adventure. I chose to figure out when Earth and Mars may align in their orbital motion around the Sun. My goal is to use a VPython model to simulate the orbital trajectories of the Earth and Mars around the Sun and predict when the two planets align. The system in my situation is the Sun centered at the origin, the Earth and Mars placed at the mean distance from the Sun on the positive x-axis. No interaction of the system with the surroundings is assumed. The result of my model was that Mars and Earth align in 781 days as predicted in my Python model. I have applied Newton's second law and universal law of gravitation to determine the positions of Earth and Mars during the orbital motion around the Sun using the equations shown, which I shall not discuss here since we have studied these extensively throughout our course. The data for the mass of the Sun, the mass of the planets, the Earth and Mars that is, and their mean distance from the Sun was obtained by the website shown that is linked over here on this page. For my VPython model, I used the mass, average orbital speed, and mean distances between the Sun and the two planets respectively to initialize the computer model. I ran the simulation iteratively to obtain enough position data over 800 Earth days. The period of revolution of Mars around the Sun is 1.88 times the period of the Earth, or 1.88 Earth years. So I wanted to run the simulation beyond one Mars year in order to find a point in time when the two planets possibly aligned. I also assumed a simplified trajectory that is circular in shape and not an elliptical one for ease of modeling. Here's my VPython code. I shall not go over the entire code here as I shall be uploading it for my peer evaluators to see. Only thing I can mention here is that the position of the Earth and Mars in its orbit around the Sun has been calculated per the same principles that we use by Newton's universal law of gravitation in our black hole lab. So I won't discuss that in detail over here. What I would like to point out is the method that I used to determine when Earth and Mars would align, if at all, during my simulation. I ran my simulation, as you can see over here, for 800 Earth days, which equals these many seconds iteratively in a while loop. And I calculated the reference angle of the Earth's position during every iteration of the while loop, which was over a period delta t was equal to the number of seconds in a day, in an Earth day. All right, and so I use the arctangent function because if you draw a position vector from the origin which the Sun was placed at to the individual planets, the Earth and Mars, you could form a right triangle and compute the reference angle of that planet with respect to the positive x-axis in this situation by doing the arctangent of the ratio of the y-coordinate to the x-coordinate of the position data of Earth and Mars respectively. I then I rounded the two reference angles to 3 decimal places and then compared the values in an if statement. If the angles were equal, then I output in a print statement the number of days that was the value of the number of days within the while loop and the angle values also. This would be the number of days that it takes Earth and Mars to align. I'll run the program and show you how. Here's a run of my Python code. I have sped it up to about 3000 speed to run the simulation fast. The orange in the center is the Sun, the blue is the Earth, and red is Mars. Let's see my output produced by Python. Here's the Python output screen that predicted time in days for Earth and Mars to align equals 781 Earth days, where the reference angle of the Earth and Mars are 1.012 radians, obviously in the first quadrant. What does my Python output mean, and how did I solve for the alignment duration? As I already discussed while showing you the code, I calculated the reference angles by using the arctangent or inverse tangent function, applying it to the ratio of the y coordinate. I am sorry, yes, it is the y coordinate of the planet's position to the x coordinate, using the right triangle method. My model predicted 781 days that it would take for the two planets to align. The real number of days as obtained from an internet source I have listed below from weather.com is 778 days. So my model did a pretty decent job of predicting the number of days within a 3-day error of margin, or a 0.384% margin of error, as you can calculate from the numbers above, with 3 days error in 781 days, and then a percent calculation. Why was my result different from the real world observed data? I assumed, or used rather, a simplified circular trajectory for both the Earth and Mars, whereas their orbits in reality are elliptical in shape. The circumference of a circle with radius r is simply 2 pi r, whereas the perimeter of an ellipse is determined by the use of the two different lengths of major and minor axes. The total perimeter of the Earth's elliptical trajectory from calculations using both the axes is 9.36 times 10 to the power positive 9 meters approximately, whereas the circumference of the circular trajectory assumed in the model by using the mean distance from the Sun is 9.424 times 10 to the positive 11 meters. Clearly, the distance the Earth in the model has to travel is longer before it completes one revolution around the Sun. The same holds true for the orbital period of Mars. Hence, the number of days taken by the modeled Earth and Mars to align in their orbit is slightly larger than the real-world observed data. I had sent the output of my Python code to a CSV file, from which I then plotted a graph from the output data of the position x coordinate of both Mars and Earth versus time. And as you can see, towards the end of my Python run, where I ran it for 800 days, just before the endpoint, you do see their position, the x positions pretty much getting close to each other, whereas this is not what I used to compare the positions for finding out where they would align, but I use more accurate angular information. I hope you have got interested in learning more about the orbits of planets around in our solar system around the Sun. I would definitely want to explore further after doing this very simplified lab under time constraints. Enjoy.